Okay, we're ready to just make a start on current of electricity, topic 10, moving along fairly quickly. First of all, circuit symbols. You should already have a fairly good idea of various circuit symbols, but what I'd like you to do, please, is draw up a list and draw the circuit symbols for these various things. You could look them up in your textbook, you could look them up on the web and so on, if you would like. This is quite a nice little way of testing your understanding. It's very easy to get into. Just look up that website there. King's College password, King's College as the login, and then just student as the password. Search for the particular activity called circuit pairs under physics, and have a go at testing your knowledge. Okay, electric current first of all, simply rate of flow of electric charge. So in terms of your notes, you need those circuit symbols, and then just the definition of electric current here, from which we have our formula I equals Q divided by T, remembering that T is in seconds, and the units are amperes or amps for short, represented by capital A. Model for electric current, we've talked about this briefly in class. Let's say we have got a whole pile of atoms, a regular arrangement, a crystal lattice of positive ions in this metal. And then we have a whole pile of electrons. I'll make them little red dots around the place. Absolutely millions and millions and billions of those electrons. If we have a switch, let's say we have a switch over here, when you close the switch, then you make this left-hand end positive, the right-hand end negative, because the electrons are negatively charged. They experience a force towards the left-hand end. You set up an electric field, so the electrons accelerate, collide, accelerate, collide, accelerate, collide, etc. Okay, and in the process of doing that, they transfer electrical potential energy to kinetic energy, ultimately of the atoms, which will exhibit itself as thermal energy. So electrical potential energy ultimately to thermal energy. What I'd like you to do in terms of your notes, please, is just take a note that conventional current flows from positive to negative. And if you don't remember, just make sure you remember that the long side of this cell here is the positive and the short side is the negative. We don't normally put those in. Okay, so just really in terms of your notes, just a note about the direction of conventional current flow, and remember that is that way simply for historical reasons. Measuring current, the device ammeter, couple of ammeters over here. With these meters, this one here has the red terminal in a thing labeled 10A, so that's specifically for measuring electric current on the 10 amp scale here. Most of the time you have the red terminal over here instead, and that applies for all the other scales there. So right, in terms of your notes, measuring current measured with an ammeter placed in series in the circuit, and it has negligible resistance. All right, so in terms of a circuit, ammeter, resistor in series. So just note those key points down there. Potential difference. We've already talked about potential difference being energy transferred over charge. V equals W divided by Q in terms of our last topic. Measured in volts, capital V, but the definition isn't this statement here. The definition is a little bit more involved in that it's referring specifically to potential difference across a circuit component. So you'll find that definition on page 104 of your dictionary, and I would like you to write that definition in your notes, please. What does it mean? You can skip this video, this particular slide, if you already understand this. 12 volts means 12 joules per coulomb. So at this point in the circuit, the charge has got 12, joules of potential energy. Well, the potential is 12 volts, 12 joules potential energy for each coulomb of charge that passes that point. Let's say that this point here is at 7 volts. Let's say this point here is at 3 volts, and that point there where all the energy, all the potential energy has been dissipated, would have 0 joules of energy, of potential energy left. So the potential difference there, 5 volts. The potential difference there, 4 volts. The potential difference there, 3 volts. You do not need to write this down. It's just a bit of an explanation. You can note it down if you find that helpful. Measuring potential difference, again, just summarize this, measured using a voltmeter connected in parallel this time, and it has a very high resistance. So note those 3 points. EMF, in your dictionary, you'll see that it stands for electromotive force. Historical name, totally wrong. So I would not really want you to refer to it as that. Please just use the term EMF. Don't expand it out. Don't call it that, please. Okay, I don't like it. It's not helpful. Okay, you'll find the definition, though, of EMF on page 45 of your dictionary. And EMF, again, is measured in volts. The difference between potential difference and EMF, well, if we have a look at this circuit down the bottom here for a moment, your EMF refers to the energy source. Your potential difference refers to where the energy is being dissipated. So in terms of that previous example, the EMF of this battery might be 12 volts, but the potential differences are the voltages across those components here. You are expected to be able to describe the difference in terms of those learning outcomes. So distinguishing between EMF and potential difference, I would like you to note down these couple of points here, okay? In a circuit then, the EMF refers to the transfer of energy, take note of this, from some other form, for example, chemical in a battery, to electrical. So other form to electrical, EMF. Potential difference, the opposite way around, from electrical to some other form, for example, heat in a resistor. So please just take note of those couple of statements. Resistance, simply defined as potential difference across a component divided by current through a component. Don't start mucking around saying, oh, how hard it is for current to flow, all that sort of thing. This formula, written in words, is the definition of resistance. From which we get then that R equals V divided by I. The units are ohms, represented by a Greek capital letter omega. So in terms of this resistor over here, we have potential difference V, we have current I that way. You will note that this arrow at this end here is pointing to the more positive side of the circuit, such that conventional current flows from more positive to more negative side of the circuit. And the resistance of that resistor then is simply the ratio of V divided by I. Important formula comes from that, and that formula is V equals I times R. Basic electricity formula, but really it is just the definition of resistance rearranged. And then a couple of examples which I would like you to do, please, in your notes. Copy out and do them. I note milliamps there, and That's about it. They should be pretty easy examples for you to do. Right, that's the end of the first little section.